Hello everyone, my name is Costa and I am going to present the work Gain a scheduled counter of a quadratic boost DC-DC converter for photovoltaic applications. This study presents the modeling and validation of a quadratic boost converter, which had not been modeled before. Also, a control system is proposed for this converter. This presentation is organized as follows. First, I will present the introduction and the main motivations of the study. Then, I will describe the converter and its modeling processes. Next, I will show the proposed control system. Finally, I will discuss the simulation results and the main conclusions. With the increasing use of renewable sources, such as wind and solar energy, many DC-DC converters topologies have been proposed. However, to ensure the compatibility of these new topologies, it is essential to model their dynamics and design proper control systems. In particular, this work studies a high-gain DC-DC converter that gives many benefits to photovoltaic systems. However, due to intermittence of PV systems, design a suitable control systems becomes more challenging. In this context, using a gain scheduled control helps handle these intermittencies and is also compatible with the nonlinear behavior of DC-DC converters. Now, let's look at the converter evaluated in this work. Figure 1 shows the converter topology, which comes from combining boost and buck-boost converters. This converter has two switches, two diodes, two inductors, and two capacitors. Its main features are high voltage gain, continuous input current, high efficiency, and compatible with photovoltaic applications. It is originally proposed to operate in continuous conduction mode, I show in Table 1, which presents the conduction states of the semiconductors. To ensure CCM, the parameters listed in Table 2 are used. Finally, the converter voltage gain I show in Figure 2. This demonstrates that the gain is always higher than the original cascade of boost and buck-boost converters. Next, the converter modeling is presented. The technique used to obtain the converter model is the small signal average model. The two operation modes of the converter can be represented in state space form, indicated by subscript 1 and 2. Then, a weighted average between both states is taken with respect to the third cycle. However, this averaging results in a nonlinear model. To obtain a linear model, the state input and output vectors are divided into a steady state component, the operator point, and a small signal component, as shown in this example. By analyzing the two converter configurations, we can obtain the following equations, which describe the behavior of the inductors and capacitors during the on and off intervals. Using these equations, the vectors and matrices of interest can be defined as shown here. The vectors and matrices. Then, applying the Laplace transform to the linear model, we can derive the transfer functions that relate the output voltage to the two inputs, input voltage and third cycle. Here are the transfer functions. As we can see, The system presents four poles. For the first functions, the zeros are purely imaginary, while the second function has three zeros. For the parameters used in this work, while three zeros are non-minimal phase, one here and a pair of complex conjugates. To validate the obtained model, the switch convert behavior was analyzed in MATLAB Simulink using a frequency sweep from 100 Hz to 10 kHz. The small signal component behaves as a sine wave with an amplitude of 0.1% of the steady state value for both inputs, analyzed one by one. The gain and phase are obtained using the Fourier transform. To ensure proper operation, the modulator frequency is away at least 100 times higher than the sine frequency. The simulation step is 100 times smaller than the fundamental period, and the last two sine cycles are used for the calculations. Figure 3 shows the obtained results, where the red lines represented the simulated switching model, and the black lines represented the transfer functions models. These results show that the model has high accuracy, both in magnitude and phase. Now, let's present the proposed control system. Figure 4 shows the diagram of the proposed control system. To increase the operation range where the converter meets the control requirements, again a scheduled control is used. In this approach, the current duty cycle is observed, and depending on the operation range, the PID controller gains are changed. In this work, two sets of gains is necessary. For the control design, the dynamics of the anti-aliasing filter are considered, and the modulator is modeled as a pure time delay. To make the converter suitable for maximum power point tracking applications with a good relative stability and operation between 20% and 100% of nominal pointer, the control requirements listed in Table 3 are defined. These requirements are specified for two duty cycle operation points, 50% and 75%. For both duty cycle points, 4 controllers is designed. For the first point, a PID controller with complex zeros provides the best performance when applied to model. However, it becomes unstable for duty cycle higher than 63%. For the second point, a pure integrator meets the requirements. Now, let's look at the simulation results. These are analyzed scenarios. They include reference variations in both ranges, input voltage disturbance, and load parameter changes. Also, the proposed controller is compared with the classical controllers. Figure 5 shows the results obtained with the gain scheduled control. The first results shows that the system maintains a proper response and reference changes with well-behaved control actions, the duty cycle. Moreover, the other results shows the robustness of the control system, the input voltage disturbances, and the load variations in both operation points. Figure 6 compares the gain schedule control with the individual controls. On the left, we have the output voltage, and on the right, the duty cycles. At first, we can see that the first range controller becomes unstable, while the second controller is too slow for low duty cycles. Also, the first gain change is aggressive, but does not impact the response voltage, while the second change is not aggressive. Finally, the conclusions of this work are presented. A dynamic model of the converter was obtained and validated in MATLAB Simulink, showing high accuracy. The proposed gain scheduled control system achieved excellent performance, rejecting disturbances and load variations. Therefore, the converter be seen as compatible with photovoltaic applications. Finally, I would like to express my thanks to the institutions that supported this work: Universidade Federal de Pernambuco, Universidade Federal Rural de Pernambuco, CAPES, and CNPq. Thank you very much for your attention.